Okay, so I believe the classroom. So I'm teaching have the some online class environment, but I think it's not ready. It's weird actually. Environment. The setting is so weird. So I'm using my laptop computer. You know. Okay, so okay, let's get started. Okay, so this is the first class of the hybrid teaching. Okay, so okay, so in the previous class we learned about the performance and then performance of the computer system, and then how to measure the performance of the processor. So actually, this is the very basic knowledge, because if you took the undergraduate computer architecture course, then I believe you already learned that how to measure the performance of the computer system. So, but you need to remember that the definition of the performance. So sometimes we ignore the exact definition of the performance, but if you perform some research, or if you perform some, if you compare the performance of the two different systems, then you need to know exact definition of the performance of the system. So usually, what is the definition of the performance? Performance is the inverse of execution time, and then so you need to know which factor decides the execution time of a system. You know, the computer is composed of software and hardware, which means both software and hardware decides the performance of the computer system. So that means the execution time. So you need to remember how to measure the execution time, and then which factor decides the execution time of the computer system. So, so this is the very famous equation that represents the execution time of a system. So execution time of the system is the instruction count multiplied by CPI multiplied by clock period. So this is clock cycle time. So you mean if you see this equation, then we can know that these three factors decide the execution time, which means the performance of the system. So usually it is, so usually the instruction count is determined by software part, like some algorithm or programming languages or compilers or instruction set architecture. And how about the CPI? CPI is the rather the architectural part, which means, so CPI can be influenced by software and hardware, so it's the architecture. So CPI is also influenced by instruction mix. So which means if a software includes the many load instructions or many branch instructions, then the performance of the software will be influenced by these kind of instructions. And then, you know, usually the arithmetic and logic instructions have fixed latency, but the branch instructions or some memory instructions have various execution cycles. So the CPI of these software can be influenced by this type of the instructions. So CPI is also influenced by instruction mix. And then also ISA. Architecture also influenced the CPI. So if we use the very high-end CPU such as the Xeon or Intel Core architecture like i7 or i5, then we can find that the CPI of this processor is low. It's because it's a CPI, the clock per instruction. But if we use the very low-end processor, such as Intel Celeron, or so it was Intel Atom, but it's renamed to the Intel Celeron. But if we use this low-end processor, then we can find the CPI of this processor is a rather higher than the high-end processors. So CPI is also influenced by microarchitecture. And then TC, the clock cycle is usually hardware part. So hardware design or hardware implementation method, and then some technology node is various technology node besides the clock cycle. So if we see that this performance equation, we can know that the performance is also influenced by software part and hardware part. So we need to focus on the advances in software and hardware part of our computer systems. Right? It's obvious actually. Also, we covers how to calculate the average performance of the many among the many performance of the many applications. So we can use the arithmetic, harmonic, or geometry means to calculate the average performance of the system. But as I showed this example, the average performance value can be changed by reference machines. So the spec benchmark recommend to the spec benchmark specified to use this geometric mean. Okay, because even though the reference machine is changed, if we use the geometric mean, then the average performance is not changed. Okay, so it's recommended to use the geometric average, but we actually in the real world, so we frequently use this arithmetic mean. So that's okay. So if you want to use the arithmetic mean in your paper or in your research work, that's okay. So it's allowed. But if we compare some performance of some new computer systems or some our advanced computer system, then we need to use the geometric mean. So just remember that if we just compare with the reference machine, and can use this geometric mean. But we can compare our idea with some baseline machine. So it's the baseline machine is the idea is not included, but we can include some architectural ideas in some in the system. Then we can compare. We can use any average method. So we can use some arithmetic mean or harmonic mean for this case, because it is compared with baseline machine, not the reference machine. But if two systems are compared with the reference machines, then we need to use the geometric mean. So Amdahl's law. The Amdahl's law is actually a very famous law in the computer system research, because Amdahl's law says that it's the only enhanced part. So the only enhanced part influence the performance of the overall system. So which means so we can divide some part of the computer system to this is the unchanged part. So it means this part is not enhanced by our new ideas or some new technology, but only this part can be enhanced. Actually, the overall performance is sadly, overall performance is determined by this unchanged part. It's what Amdahl's law says to us. So, and then, but we need to focus on the fraction of this enhanced part if we want apply some new ideas or apply some new technology on some computer system, and we need to focus on some fraction of the part which can be enhanced. Okay, that's what Amdahl's law said. So, but actually, the Amdahl is the name of the researcher, and then this Amdahl's law focused on the multi-core architecture. So which means the software, the application can be split into some serial part. So this part cannot be enhanced by multi-core architecture. And then application also has the parallelizable part. So if we apply the multi-core architecture, only the parallelizable part can be enhanced. So that's what Amdahl's law says. So if we apply the multi-core architecture like dual core or quad core, even the core, then we can expect that the performance of the computer system can be enhanced by number of times of number of cores. So, for example, if we apply the dual core architecture, then we expect that our computer system can be the performance of our computer system can be enhanced by twice. But it's not true because our software is composed of serial part and then parallelizable part. Only this parallelizable part can be enhanced by multi-core architecture. So, but I said that this Amdahl's law is somewhat pessimistic. So it's based on the pessimistic assumption, so which means that with the Amdahl's law assumes that the problem size is constant, which means even though the multi-core architecture is applied, this parallelizable part is not changed. So only this parallelizable part can be enhanced. So if the Amdahl's law is applied, this is some number of cores, and then based on this fraction of the parallelizable part, then we can know that the performance is saturated around 2, even though we increase the number of cores to about 20. And actually it's very obvious because Amdahl's law is very simple, so we can easily calculate the expected performance using some multi-core architecture. But I said Amdahl's law, Amdahl's law assumes that the problem size is constant, but it's not true actually in the real world. So if we apply the multi-core architecture, then the problem size applied to this multi-core architecture can be also changed. So that's what Gustafsson law says. So in the Gustafsson law, this is the execution time. The execution time in the Gustafsson law, execution time is also defined as the serial part and then parallelizable part. But Gustafsson assumed that this parallelizable part can be increased with the number of cores. So that means the problem size can be changed. So when the Gustafsson law is applied, the performance is enhanced linear. The performance of the new computer system is the multi-core system is proportional to the number of cores. It's actually because the parallelizable part is also proportional to the number of cores. That's what Gustafson says. But so you need to think like this. In the real environment, real usage environment, how you need to think how users run their computer systems. So which means, so actually, if we use some fixed benchmark, such as the spec benchmark, so which means the problem size is fixed. Then the Amdahl's law is true. So we can apply the Amdahl's law based on the Amdahl's law. But in the real environment, so like the server computer system or data centers. So in the data center or server systems, many different applications run on this system concurrently. And then if we apply the multi-core architecture or some more core systems or parallel systems on this data center or server systems, then the problem size also increases because many applications run on concurrently. So then the Gustafson law is true for this kind of system. So if you do research, then you need to apply some. Actually, in the research paper, then you need to compare the performance of the enhanced system with the baseline system. But based on some assumption, that means that assumption in some problem size or assumption in some workload, your performance, your result can be different. So which means, so if you want to apply your idea on some server systems or multi-core architecture, but if you just apply the Amdahl's spec benchmark based on the Amdahl's law, then your performance gain can be very small, and it will not be accepted to the conference or journals. So in this case, you need to define some appropriate workload or appropriate usage environment for your research. Okay. Okay. So actually, I posted Amdahl's original paper on the Piazza. So if you're interested, you can read the paper. So if you click on this link, it's Gustafson law, then you can find also paper by Gustafson. And then, okay, let's think about the Amdahl's law in the multi-core era. So this is the typical cycle for computer system and then software enhancement. So we start from the slower program. So if the execution time is very long and the performance is very low, then we need to increase the performance of the system. But this is the workload. So this is the existing workload. So if the workload is slow, then we focus on the hardware system. So we need to enhance the performance of the hardware system. So performance of hardware, the performance of computer system is enhanced, so we can use the faster. That means we can use the high performance machine. Then we can reduce the execution time of some existing workload. So if the computer becomes faster, software developer makes the large application, so it can use this fast machine. So the application also gets more complicated, more complex, more applications become heavier. Also, as the hardware is so good, then these large applications are developed by the large development teams. Also, we apply the very large number of abstraction levels to the software, which means the software becomes heavier and heavier, then performance is also decreased because the software, the workload gets heavier, so it becomes the slow program. So this is some software and hardware development for the single core era. So which means actually every CPU was a single core before 2000. So in order to use the good computer, then we need to use the better single core, so better single core system. But recently we are most of the CPU has multi-cores, that is the multi-core architecture, and so we can exploit these multi-core systems. And how can we apply the Amdahl's law? So multi-core, if we apply the multi-core hardware, so actually the Amdahl's law starts from the very simple assumption. So which means if we apply the multi-core architecture, then we can first include the more cores, the more same cores. So that means that the performance of this single core is the same, but we can include the more cores. That's what Amdahl's law assume. But the single core performance, the performance of the single core can be also advanced. So we can apply the very more enhanced core for the single core. Then we need to also consider this performance of the single core. Okay, even though we can apply some multiple cores. Also, if we apply our idea, then we need to also consider cost. So which means if we apply the more resources on our single core, then we can make the better single core, but this single core will consume more resources, such as area and then manufacturing cost or even power. So this is the cost consumed by advanced core. So we need to also consider the cost, which is also required for your research. So if we apply your new idea on some baseline system, then you need to also consider the cost by new idea. So the performance can be improved by your idea, but also cost can be also increased by your idea. So if this increment is larger than this performance improvement, then your idea will not be applied to the real system. So actually this paper, Amdahl's law in the multiple era, is the paper written by Mark Hill. So he is a very famous architect in the computer architecture research area. Actually, he is also very legendary people, okay? Legendary researcher. So we can increase the performance of a single core, but also we can apply the multi-core architecture on our computer system. But the scalability matters in the multi-core architecture. So which means even though we apply the multi-core architecture, the performance enhancement will not be will not be proportional to the number of cores. So it is called the scalability issue. It's a scalability. Okay, so which means even if we use the 2x core, but the performance cannot be, it's less than 2x. That is the scalability issue. But the Amdahl's law, the scalability issue is not considered. So actually, we need to consider some scheduling issue and synchronization issue, and some communications between the two cores. The multi-core architecture is actually very complex, but this avoid is just ignored in the Amdahl's law. So in the Amdahl's law, if we just apply the n cores, we assume that the parallelizable part is the execution of the parallelizable part is reduced by f divided by n. So this is the typical Amdahl's law. It's the Amdahl's speed up, but the Amdahl's law is published in 1967. It's a very old law. But Amdahl's law still works in the contemporary computer architecture research. And so you need to remember. So Amdahl expects that this 1 minus f, so which means the part which cannot be enhanced. It's about the 35%. Then if we just apply the 4-core processor, it's a quad-core processor, the speed up is just 2, and then if we just apply the infinite number of processors, which means infinite number of processors for the parallelizable part, the speed up is less than 3, because 1 minus f. So this fraction is about 0.335. So Amdahl's law says that multi-core is not necessary. Okay, so Amdahl's law just says that it is very important to increase the performance of a single core. So it's not so applying the multi-core is not a good idea. That's what Amdahl's law says. But it's also true for the multi-core era, but no. We need to consider the multi-core architecture. And then everyone knows that. So recently, everyone knows that multi-core architecture is essential. So currently the GPUs are very famous because we can run batch of thread concurrently in a GPU architecture. So actually, the GPU architecture is very good for executing parallel applications, which means, the GPUs have hundreds to thousands of cores, which means we can run 100 to 1,000 threads concurrently in GPUs. So we know that the multi-core architecture is essential architecture in the modern computer systems. But Amdahl's law says that, multi-core is not required. It's very pessimistic. So how can we apply the Amdahl's law in the multi-core era? So actually, this paper was published around 2010, maybe around 2010. So it's already the multi-core era. So this paper consider how to apply Amdahl's law in the multi-core era, because Amdahl's law is also very important law in the computer architecture research. Okay. So when you apply the Amdahl's law, then we need to also consider the cost of the new system, cost of the new processor. So actually, we need to also focus on this cost. Okay. And then this paper started from the base core equivalent, called the BCE. So actually, this paper just assumed the area cost. So which means the chip area is fixed, but we can apply more enhanced core if we use the larger core. So, and then also we can include many small cores. So I will explain later. So in order to explain the cost of the single core, this paper assumed the one base core equivalent. It's called the 1 BCE. So you can think like this is just a unit of area cost. Okay, so this is the one one BC is defined in the paper. And then the researchers assume that the performance by this one BC core is just one. It's a normalized performance. And then if we apply the more enhanced core, so it's the advanced core, then we need to invest more resources on this core. So we assume that we can assume that this core, the enhanced core, have RBCE. So that is the resources consumed by enhanced core. So we can say that this is the BP core. Okay, so more some advanced core. Okay, if we invest the R resources, the R times of the resources, then we can say that performance is the proportional to this cost. We don't know actually. So if the cost is proportional to the performance, then it's very happy actually. So this is called the function of the performance by. So actually the researchers assume that the performance define the performance function. So this function receives the R, the cost of the core, as argument. Okay, so it's defined as the curve, and R. R is the input of this function. So we need to consider the cost of the advanced core, and then the performance by this advanced core in this multi-core architecture. So usually, the researchers explain about the three different cases. The first case is the performance of R is bigger than the cost R. It's a very happy case. It's the most happiest case actually. So performance is enhanced. It's more than the invested cost. So it's very it's a very good case, but in real world, so we cannot see this case actually. So even though the performance is same, performance is proportional to the resources, and it's also happy. So we can apply the very large core actually in this case. Then we can always increase the performance with this very large core. But in reality, the performance is it's already true actually. The performance enhancement is usually it's less than the cost of the processor, the invested cost of the processor. Okay, so we need to assume that the performance is less than the R. Okay, this function is less than R. It's not proportional. And then in this paper, the researchers assume that the performance of the BP core is enhanced core is equivalent to the square root of R. So what is R? R is BCE. And the R means the R multiplied by BCE. So which means if we apply R times of resources on the BP core, the advanced core, what the performance is of this core is about the square root of R. Okay, it's just assumption, but it's usually true. Okay, that's why this paper is published in the public. So how can we apply this cores, multiple cores in the fixed chip area? So this slide shows the three possible cases if for applying symmetric cores, which means we can include multiple cores in the same in the one chip. It's a fixed area, but we can apply the same multiple cores. It's a symmetric cores. Okay. So let us assume that the entire resources in a single chip is the 16 BCE. Okay, so it's a 16 BCE. So in this case, if we just apply the symmetric multi-core architecture, then we can apply the 16 1 BCE cores, so which means 16 WIMP core. Oops, what happened? So we can apply the 16 WIMP core. So WIMP core means that it's the low performance core, low end core. Also, we can apply the 4 BCE core, so some middle end core. Also, we can apply the very large, very big core, the 116 BCE core. So we can think 3 different configurations with the symmetric multi-core architecture. Then, how the performance is applied for this symmetric multi-core architecture. So this is actually, we can say that this multiple WIMP core architecture is very similar to GPUs, because GPU has very large number of cores, but the performance of each core is very, very low. About this 4 BCE core is similar to the in the core architecture. So usually the core architecture is very good. Core architecture is very good, a BP core. This is a single core system, single core architecture, and then it's a common mid-range architecture. So if we just apply the Amdahl's law for these different configurations, how the performance is improved. So we assume that the performance of RBC core is the perf R. So which means if we use the enhanced core, then the serial part of the applications can be also improved. So which means in the Amdahl's speed up, this factor is also improved. And then if we just apply the RBC core, then what is the number of cores? The number of cores is the N divided by R. Okay, so which means, so this is the N is the 16 BCE, and then if we apply the 16 BCE core, then number of core becomes the 1. Okay, because so number of core is a parallelizable part is the N divided by R. So this is the performance by parallelizable part. Okay, so we can also reduce the execution time with the multi-core. Also, the execution time of the single thread is enhanced by perf R. Okay, so this is the some new speed up, new Amdahl speed up in the symmetric multi-core architecture. Okay, and we can draw a graph, the speed up based on the F value. The F means the fraction of the parallelizable part. Okay, it's the parallelizable part. So why is it so big? So if we apply the So if the F is just 0.5, which means that only the half of the workload can be parallelized. So this is the speed up by number of cores. So actually the configuration. So if we just use the 1 BC core, then we can include the 16 cores, 2, 8. So it's very simple. Then the graph looks like this. If F is 0.5. So what happened? So in this case, which means the F is just 0.5, then the speed up is best if we apply the 1 BP core, 1 enhanced core. Okay. So then the speed up is about the 4. Because this is just a single core, and then the performance is improved by 4. It's obvious, actually obvious. So we can apply the different fraction of the parallelizable part. Like if F is 0.9, then the maximum speed up is about here, so which means that the number of core is the 2, and then so the graph looks like this by the fraction of the parallelizable part. So if this so modified Amdahl's law is applied to the multi-core architecture, and then if we just consider the performance and then cost of the multi-core architecture first time, then we can say that based on the fraction of the parallelizable part, the best configuration. The best configuration can be also changed. So now, which means that number of cores and then number of which core will be used for the symmetric multi-core architecture. But you can say that this enhancement is determined by F, which means the fraction of parallelizable part. So that's why the workload characteristic is very critical for some configuration performance of the entire computer system. Okay. Okay. But we can think like some very extreme case. So which means that, so in this slide, so here we assume that N is 16 BCE. But you know, the Moore's law is applied. So what is the Moore's law? Number of transistors doubles every 2 years. So which means in the same area, we can include more transistors. So which is very similar to the cost. So in this paper, the researchers assume that the cost is determined by area. But if Moore's law continues, which means number of transistors doubles every 2 years, then which means in the same area we can include more transistors, which means we can invest more resources for cores. So which means N will be increased. So its available resources are increased. So if Moore's law continues, then we can achieve the 256 BCE in the same area. And what will happen? So also, if we assume that N is 256, that is the 16 times of the original assumption, it's a 16 BC, right? And how about the graphs? The graph shape is changed, but also is changed by the fractions. So, but we can say that optimal number of cores and speed up can be also changed by this number, the total resources. So for example, if the F is 0.9, the R is the 28. So 28 out of N is 256. So if the N is 16, when the F is 0.9, the maximum speed up is when the R is 2, okay? And the speed up is about 26, then it's higher than the 6.7 actually. And then if F is 0.99, the speed is about 80, okay? So what does that mean? With the same workload characteristics, but if we can invest more resources in the single chip, then we can the optimal configurations. So optimal configuration can be changed. Okay. So if F becomes the 0.999, then so in this case, most of the part is parallelizable. So it's actually the number of core is the 256. It's the very small core, very wimpy core, but many very large of wimpy cores are applied, so included in the single chip, then we can achieve the very high performance in this case. So, you know, this is very similar to the GPUs. Okay, so it means that the why GPUs are good for the parallel execution, parallel applications, because in the parallel applications, F is very high. So in this case, with the Amdahl, with the Moore's law, now we can include more transistors. So actually, you know, the GPU chip is one of the largest chip in the world. So which means the one GPU chip includes many transistors. So if the workload applied the GPU is most of the parts are parallelizable, then it's good for applying very wimpy core, large number of wimpy cores in this case. Okay, that's why the GPU is good for parallel applications. But if the parallelizable part is small, even the part is about the 0.9, it's not small, it's very high, but it's 0.9. So the serial part is just the 0.1. So in this case, if we apply the many cores like R is 28, in this case, we can achieve the very high, the highest speed, highest performance. So it's very similar to Xeon core. Right. So recently, Xeon includes the 20 to 30 cores. So it's okay. So the Xeon is applied to the server system. So what does that mean? So based on the characteristics of the workload, then we can apply the different configurations. So it's something like, so we can apply the large number of wimpy cores. Also, we can apply some tens of cores or some mid-range or BP cores. Okay, it depends on the workload, and then it depends on the fraction, actually, the fraction of parallelizable part. So it's very interesting. So based on this, so Amdahl's law is very simple. And then if we just consider some cost and then some technology trend like Moore's law, then we can pick some very optimal configuration of the multi-core architecture based on these assumptions. So for example, oh, this is the GPU. Oh, this is the Xeon. So we are actually the processor vendors developed their some new cores or some their new architectures based on these assumptions. Okay. Okay, and then another possible configuration is the heterogeneous multi-core architecture. So it's an asymmetric multi-core chips. So it's very similar to the little bit of the ARM architecture, big little bit, or it's also very similar to the Elder Lake architecture of the Intel, the most recent Intel architecture. So which means the WIMP cores and the PP cores are mixed in a single chips, and how the performance is enhanced. So if we apply the heterogeneous architecture in the multi-core processors, then the configuration is a little bit more complex. It's more complex than this symmetric core architecture. You know, with the symmetric core architecture, we can consider the very simple equation like this. But if we apply the heterogeneous architecture, so asymmetric multi-core architecture, then this architecture may have the small number of PP cores and then many WIMP cores like this here. But we need to also consider the cost of the entire single chip. So the configuration is more complex. So in this case, the researchers just assume that we can include only one PP core and then plus other WIMP cores here. So then, which means the assumption gets simpler. Okay. So that is the enhanced and that's speed up by this configuration. Okay. And then if we apply the this Amdahl speed up for the heterogeneous core multi-core architecture, then the graph looks like this. So you know, if we just include the one BP core and then another multiple WIMP cores for the parallel execution, then graph shape of the graph also changes. So based on this RBC for the multi-core, then we can also find some optimal point over here. So let's compare the overall speed up by this heterogeneous architecture, the symmetric multi-core architecture. If F is 0.99, R is 41. And then how many cores? How many WIMP cores? It's a 216. So if we just compare with the symmetric multi-core architecture, then R was 3, and then the number of cores was 85. And how about the speed up? It's 116.6 versus 80. So which means also it is influenced by characteristics of workload. Okay, so F is 0.99. We can find that if F is very high, it's about so R becomes the 8. But if F is just 0.999, R becomes the 41. In this case, speed up is 166. What does that mean? Small fraction of the serial part. But if we can apply a symmetric core architecture, the heterogeneous multi-core architecture, then we can achieve more speed, higher speed up. we can achieve a higher performance in this case. So it's very similar to the recent big needle ARM architecture and Elder architecture. Okay, so BP cores and then WIMP cores are mixed in a single chip, and then we can achieve the higher performance. Okay. So actually, the main purpose of this heterogeneous architecture is to reduce the power consumption in the system, because the BP core consumes much more power compared to the WIMP cores. But so actually, the main constraint was the power consumption. But if we just consider the performance using the very simple Amdahl's law, and we can see some benefits by this heterogeneous symmetric multi-core architecture. Okay, like this. So it's very, even though this paper is very old paper, but this old paper can give us some ideas or some potential ideas for us. Okay, so we can apply actually the Amdahl's law is a very old law, and then it's a very simple law. So you know the Amdahl's law is very simple, it's very easy. But Amdahl's law just can also give us some ideas, some technology perspective for some future trend or future configuration of the core architecture. So how can you apply the Amdahl's law now? So recently, domain-specific architectures are very popular because the problem is that, so actually, so in the previous slide, we assume that Moore's law continues. So if Moore's law continues, then we can include more resources in the single chip, then we can make use of these more resources for the more cores or some more enhanced cores in the single chip. The problem is that the Moore's law is ending. So that means it's very hard to apply the more advanced semiconductor technology in the CPU or processors. And then that's the problem. How can you apply the Amdahl's law currently? So currently, we are the domains. That's why the domain-specific architectures are very popular, and then many researchers have interest in these domain-specific architectures. So actually, the very popular domain-specific architecture is the GPU. You know, the GPUs are designed for accelerating graphics applications. It's a domain-specific applications. But recently, the GPUs are widely used for parallel applications such as machine learning or neural networks applications. Well, this GPU just focuses on the specific domain of applications. So, which means we can just increase this domain of application. So this is called the accelerators or domain-specific architectures, but we can apply Amdahl's law for these domain-specific architectures. So think like this. Why do we use GPUs? Why GPUs are very popular recently? Because more and more people want to run machine learning, neural network applications. That's why GPUs are very popular. And then actually the data center. In the data center, many data center vendors try to apply these neural networks or machine learning applications in their data center applications, which means the fraction of these parallel applications are increasing. So if this part is increasing, then we can apply different architectures or different configurations in the system or processors. So, which means F is increasing in the Amdahl's law. In the Amdahl's law, the F is just a parallelizable part, but we can say that this is the fraction of the workload which run on the data center, but and then we can say that the F is the fraction of some parallel applications or the parallel applications. So if F increases, then we can apply the different configurations. So if we just apply the symmetric multi-core architecture, if F becomes 1, and like so F is very high, then GPU is good. Okay. So we can say that F is the fraction of the some specific domain software. Okay. So if F becomes higher for the specific domain of software, then it's good for applying accelerators. Okay, accelerator. So that's why some domain-specific architectures are very popular recently. Okay, so you can also apply the Amdahl's law, the current trend of the processor research. Okay. Also, I also post this paper on the Piazza. It's on the slow in the multi-core era by Mark Hill. So you can visit this site for the more information. Okay, so let's take a break for 10 minutes. And then any questions for this topic? Okay, let's take a break for 10 minutes, and then I will be back at 11:43. Okay. Oh, my battery is low, 48%. The mic was off. Okay. Okay. So unfortunately, I turned off the mic. 그죠? Okay. Okay. So actually, it's not easy to have it's not easy to have a hybrid teaching, online and offline mixed teaching. But I believe yes. So the in-person lecture is more effective, and then hopefully. But if you participate in this lecture proactively, then it will be more effective. Okay. Okay. Yeah. So it's not easy actually. So because so I think we are facing a very hard time because due to the COVID-19 pandemic. So we are facing a very difficult time actually. But so hopefully this difficult time will pass soon. So I don't know, but 해야죠 어떡해요. Okay, so now I will talk about the impact of technology in the process architecture and the processor some development. So the CPUs are, or GPUs, the processors are build-side chip. So which means if we make processors, then this processor is the product of semiconductor technology. So, so actually, I believe some of you already see some photo of the wafer die. So actually, the Intel processors are fabricated on the surface of this silicon wafer die, and then we just cut this wafer to some rectangular forms, and then these small chips are fabricated in these chip packages. So it means the semiconductor technology also decides the performance cost of processor. So in order to understand the performance and cost of the processor, then we have a basic knowledge. We need to have a basic knowledge on semiconductor technology. So in this time, in this class, I will discuss about the semiconductor technology in the processors. So technology challenges. The most critical cost and the most critical constraint in the processor is power consumption. Okay, actually, why do we use multi-core architecture? The performance is also important, but actually we use the multi-core architecture due to power constraint. So actually, the power consumption of the processor has two different components. It's dynamic power and static power. Static power, it can be called leakage power. So usually in the undergraduate course, we explain the dynamic power only, because in the traditionally, the dynamic power consumption was very dominant in the processor's power consumption, but recently the static power is also critical in the power consumption of the processor design, which means the static power, recently the static power consumption occupies around 42 and even more than 50% of the entire power consumption of a processor. So this is the equation of the dynamic power consumption and then static power consumption of a processor. It's very popular. This is actually the very popular equation. The dynamic power consumption of a processor is alpha. Alpha is the activity factor. So activity factor. So which means somehow the signals are frequently changed in the processor. So usually this activity factor is the constant for every processor, because actually so we assume that the activity factor is around the 0.5, because actually in the CMOS circuit, the circuit is turned on and then turned off and repeatedly. Okay, and then C is the capacitance. So capacitance. So it's called the actually capacitance. So capacitance is proportional to the area of chip. Okay, so if you took the electric circuit course, then you can remember that the capacitance is proportional to the area of the metal plate, and then also actually it's a area divided by this D. So actually every circuit has the parasitic capacitance. So actually the electric charges are stored in this parasitic capacitance. Okay, so capacitance is proportional to the area of the chip, and then V means the supply voltage. So it's called the VDD. In maybe around 30 years ago, 30 to 40 years ago, the VDD was about the 5 volt, but recently the supply voltage to the CPU is around the 1 volt. Okay, it's very low recently. And F means the clock frequency. So if we just see this dynamic power consumption of the processor, then we can say, oh, C is a proportional to the area, is a supply voltage, and then F is the frequency. So actually, and then I also said that the power constraint is very critical for the processor design, because the power consumption is determines the running cost of the processor. Also, the power consumption decides the manufacturing cost of a processor. Actually, the heat from the processor is determined by power consumption of the processor. So it's also related to the cooling system of a computer system. Okay, the power is very critical. Also, the power consumption decides the package level of the CPU processor. So power is it's a critical cost. It's money. So if we see that this power consumption equation, especially dynamic power consumption, then we can say that, oh, it's proportional. Actually, we cannot change the activity factor. It's really constant, but if we can change the C, capacitance, V, and the F. Okay. But if we just see this, actually, with the same technology node, it's the same semiconductor technology node, we can say that the supply voltage is proportional to the clock frequency, which means that in order to apply higher clock frequency, then we need to apply higher supply voltage. So if you are interested in overclocking, then how can we overclock the Intel CPU or AMD CPU? The first, we need to increase the supply voltage to Intel CPU, right? Then we increase the clock frequency applied to the CPU. So which means in the same technology, in the same semiconductor technology, the voltage is proportional to clock frequency. So in this equation, it's a C V square F. So actually V is proportional to F. So which means dynamic power is proportional to cube of frequency, clock frequency. So what does that mean? So actually, in a traditional CPU design, the dynamic power consumption was very critical. So as I said, that it's very critical. So it is related to running cost, manufacturing cost, also thermal, and then many issues, many other costs. So, and then we know that P is proportional to cube of frequency, clock frequency. So, which means it's not, if we consider the power consumption of the processor, then it's not good. It's not good to increase the clock frequency of a processor. So let's see the performance equation. What's the execution time is the instruction count, CPI, and then T. Actually, T is the 1 over F. So, and then, the execution, the performance is the 1 over execution time. So which means the performance is proportional to the clock frequency. So if we just focus on the hardware design, we increase the clock frequency, then we can increase the performance easily, if we increase the clock frequency. But that's good. way to increase the performance of a processor. But in order to increase the performance by F, then the power consumption, dynamic power consumption of the processor is increased by F cubed. So that's very critical. That's why we cannot apply very high performance single core recently, because I said the best way, actually the easiest way to increase performance is to increase the clock rate, clock frequency. But in order to increase the clock frequency, then we need to consume F cube of F cube. So it's exponential. The power consumption increase exponentially. So if we just consider the dynamic power, then it's not increasing the clock frequency is not a good idea. So that's why we are using multi-core architecture. So I said that, so you can apply the multi-core architecture to increase the throughput of the computer system. But actually, we apply multi-core architecture due to power constraint, the power consumption issue. So if we just consider the dynamic power, the multi-core architecture is the good solution. But I said that recently, the static power is also critical. So static power just occupies the nearly half of the entire power consumption. So let's see the static power equation here. If we see the static power equations, so this is the A, B, I sub, which means, so what is the static power? So actually, the CMOS transistor circuit looks like this. So it's an inverter circuit. So for example, it's a PMOS, and then this is NMOS transistor, and then this is the VDD, and then this is the ground. So this is the inverter circuit of the CMOS transistor. Actually, the CMOS transistor is it works like switch. So based on this gate voltage, the PMOS is turned on and off. Also, NMOS transistor is turned on and off. So sometimes, so I said that every circuit has the parasitic capacitance here. So based on the on and off of these switches, the PMOS and NMOS, this parasitic capacitance is charged or dissipated. That's how CMOS working. So, but usually, if the PMOS transistor is off, then NMOS transistor is turned on. And then also the opposite case is true. So if the PMOS transistor is turned off, then NMOS transistor is turned on, the NMOS transistor is turned off. So if we just focus on the path from VDD to ground, this is the major path from VDD to ground. This path is disconnected. No? Because one of the PMOS transistor is off, PMOS is off, then NMOS is on, and PMOS is on, the NMOS is off. And then this path is usually disconnected. During the very short time of this path is connected, usually disconnected. That's why the CMOS transistor is better than the very traditional BJT. Some other BJT transistor. But slightly very low current can pass through this VDD to ground path, even though one of the transistor is turned off. It's called the leakage current, and then the static power is caused by this leakage current. So this current is called the substrate current. So I sub. So And then for the power equation is the voltage multiplied by I. So VDD is the supply voltage, and then this is the substrate current. And then the static power is determined by supply voltage and the substrate current. A is the constant. And we can apply this part for this substrate current. So static power is determined by supply voltage and then this current. And then if we just rewrite this current, substrate current, then we can say that E minus E powered by minus K, it's threshold voltage divided by temperature. Okay. So, but traditionally, the fraction of this static power was very low. So we just focused on the dynamic power of a processor. Recently, the static power is very large. So I said it's around 40 to more than 50% of the entire power consumption, because of the transistor node, the transistor size becomes very small. So we cannot entirely off this transistor, the PMOS or NMOS transistors. So that's why the leakage current is very large recently. So which means even though the software does not run, the software is not running on the processor. The processor is just turned on, but nothing is running on this processor. But this processor just consumes power because of this static power. And then around the 50% of power is consumed by this not working processor. It's a very serious problem. Okay, the power consumption is the very serious issue in the processor design. And then also recently the leakage power consumption is a very serious issue. So if we see that this leakage power equation, we can find, we cannot change the A, this part. A is the area, sorry. So A is the area, because actually this static power is proportional to the number of circuits. So the size of circuits, the number of transistors, which means the static power is proportional to the area, and then supply voltage, and then this current, leakage current. Actually, if this is the supply voltage, and then actually this I, the leakage current is influenced by this threshold voltage and temperature, the working temperature. So if we see that this static power equation, we can find that a static power equation does not include any clock frequency factor, which means it's not related to performance of a computer system. Okay. The performance of processor is proportional to the clock frequency, but if we see that this static power equation, we cannot find any clock frequency. It's not related to performance. It is related to actually area. Okay. Also, this static power is highly influenced by threshold voltage of the CMOS transistor, and then temperature. So, but we cannot control this temperature in the processor. So, actually, the A and then the threshold voltage is the very critical factors that determine the static power of the processor. So how can we reduce the static power? So that means if we apply, so if we build smaller chip, so that means that if we reduce the number of transistors, which is included in the single chip, then we can reduce the static power, because the static power is just proportional to the number of transistors. And if we reduce the number of transistors, then so we can reduce the static power. Oh, it's good. But so we are living in the multi-core era. So we prefer multi-core architectures because the multi-core architecture is very good for the performance and then some the recent applications. So it's a good solution. So we need to include more transistors in our chip, process chip. And how can you handle this static power? That's why the static power is the very critical issue in the recent processor chip design. Okay. So you need to remember that traditionally the dynamic power was critical only, but recently we need to consider both dynamic power and static power in the processor design. Okay, so I said that power is the very critical problem because as I mentioned, the power is a critical constraint in the chip design, and also the power determines the many cost factors such as the running cost, manufacturing cost, or some thermal management cost. Okay. Also, actually, the power consumption of the processor is tightly related to the temperature. Then the temperature is very critical. So I believe some of you have heard about the recent issues in the Samsung mobile phone. So it means in order to decrease the temperature of the processor, the Samsung applies some patch which limited the performance of the processor. Because if the temperature is very high, then the circuit can be destroyed. So that means the CMOS circuits can be destroyed. That's a very critical problem. Also, another issue is that in order to avoid this situation, we need to reduce the power consumed by a CPU, which means we need to limit the performance of the CPU. That's why Samsung applies the switching software to limit the performance of the processor, and then it becomes the very critical issue, a popular issue in some Samsung smartphone. Okay, because temperature is also very critical. So we need to maintain some appropriate temperature level to run the processor. And then energy. And what is the energy? Energy is actually power multiplied by delta T. It's the execution time. So actually the energy is the total amount of power consumed during the application is executed. Okay, so actually energy is the integrated power. So for example, actually the energy is very critical for the mobile devices. So we also need to consider the energy consumption. So think like this. So in the CPU A, is a CPU A and a CPU B. CPU A is very fast. It's fast, and then this is very slow. So, but CPU A is about have the 2x performance, the higher performance than the CPU B. So that means that the CPU can complete the same application with the half execution time. But if the power consumption of the CPU is about the 1.5, and then if the power consumption of the CPU B is the 1, what is the energy? So energy is the required power to execute some application. So that means that the required integrated power means that the power, required power from start to the end of execution. So if we just simply calculate the energy of the CPU A and CPU B, this is the 3. This is the power is 1. Not it's a 3 because it's fast. Sorry. So execution time is for the CPU A is 0.5, and the execution time of this is the 1. Oh, it's not easy. Then what is the energy? Simply the energy for the CPU A is the 1.5 multiplied by 0.5 is the about 0.75, right? And then how about the CPU B? It's 1. So, if we just compare the energy, so energy means some total required power for from the start to the end of the execution. So if we just compare the energy, which one is better? CPU A is better. Even though CPU A consumes more power, but CPU for the aspect of the energy, then CPU A is better because CPU A is faster. Actually, when we consider the power consumption, that is cost, and then if we just consider the cost, then we also need to consider the execution time. The execution time for the workload, for the same workload. Okay, so that is the energy. So which means in order to complete the same workload, CPU A consumes the 0.75 of energy is the running cost, but CPU B consumes the 1 energy. It's also cost issue. So if we just consider the running cost for executing the same workload, then we need to focus on the energy. Okay. So energy is the power multiplied by execution time, and then this is related to running cost issue. Also, the energy is critical for the mobile devices because the mobile devices are working with the battery, and battery has limited electric energies. So we need to focus on the energy for these mobile devices. Okay. And then reliability. What is the reliability? Okay. So we assume that actually, what is the benefit of the system design? Digital system. The data of the digital system is just 1 and 0, which means that this signal is not influenced by, so usually it's not influenced by noise, so electric signal noise, which means the data is not changed usually. Then what is the reliability? What is the reliability issue? So we assume that the DRAMs and then some storage digital component. So we just use the 1 and 0. It's the digital signals. But actually, what is that? We live in analog world, so which means the 1 and 0 of the digital signal is just determined by voltage level. And then what voltage level actually is determined by the voltage level determined by the stored charge in the capacitor. So this is the capacitor, and the electric charges are stored in these capacitors. And then if the amount of electric charge is high, is large, then the voltage level is high, which means it's 1. And if the amount of electric charge stored in the capacitor is very low, then voltage level is low, which means 0. So actually, the data stored in memory components, so the data in the digital circuits are determined by amount of electric charges. Okay, so which means, so actually, the benefit of the digital system is that it's the voltage level, but based on the threshold voltage, so if the voltage level is higher than the threshold voltage, we can say that, oh, this is 1. If the voltage level is low, then lower than the threshold level, then it's 0. But usually, the voltage level by some input signal looks like this. So we can say that, oh, this area is very small. So the data is not influenced by electric noises. Okay, that's the benefit of data system. However, the transistor size is very small recently, which means the memory cell size is also very, very small. So which means the memory cell, the size of the memory cell determines the amount of charge stored in this cell, this memory cell. So for example, so think like the DRAM. So how DRAM looks like? So this is the DRAM cell. Actually, the electric charges are stored in this capacitor. Okay, if the size of the DRAM cell is decreased, which means the size of this capacitor is also decreased. So I also explained that the Q, it's a capacitance. Capacitance is proportional to A, and then it's inversely proportional to this thingness of the capacitor. So if A is reduced, the capacitance is also reduced. So which means the amount of charge stored in this capacitor is also reduced. Then what does that mean? These electric charges, the amount of electric charges can be easily influenced by electric noises. And then, so we cannot see this cosmic ray from the space, but the cosmic rays, some particles are now hitting our devices currently. We cannot see this some cosmic rays or some particles from the space, but these particles are currently hitting our devices. And then if these capacitors are hit by some alpha particles from space or some cosmic rays from space, then this voltage level in the capacitor can be fluctuated. So it can be changed. So because this amount of charge is very small, which means this amount of the voltage level can be changed by small amount of particles, alpha particles from space. So which means the DRAM data can be changed. So this is the reliability issue. Okay. Also, we can say the reliability issue that the digital circuits can generate the incorrect data, or the memory devices, the data stored in memory devices can be changed, which is called the reliability issue. And it's very critical for with the modern semiconductor technology, because as I mentioned, if the size of a transistor becomes smaller, then the charges, electric charges stored in this CMOS transistor is also reduced, and then it can be more influenced by noises. That's why reliability issues are critical. So we can distinguish that this reliability issue as the transient failures. So it's called, sometimes it's called the soft errors, or intermittent failures, so temporary failures, or permanent failures. Okay. So as I mentioned, so we will also learn about the reliability issue later. And then, as I mentioned, these transient failures are influenced by some particles or cosmic rays from space. 우주에서 떨어져요. So the data can be changed, but it's very, just the data is changed. The circuit is not broken. Okay. So this is why this is called the software. Okay. But the circuit can be broken. What does that mean? So actually this, okay, so some defect can be included during the manufacturing. So this is some manufacturing defect, so, but reliability does not handle this manufacturing defect. But our circuit, the CMOS circuits can be worn out. So worn out means that, so it's obvious to the real world that every materials are worn out. So worn out means that 낡아서 헤어지다 이런 뜻이죠. So worn out. So if we use some circuits very frequently, and then if we use this circuit for a long time, then the CMOS circuits can be worn out. It's broken. So this is called some temporary failures or permanent failures. So if we use our processor chip for a long time, the performance, the clock frequency, so which means the speed delay of the, the system. Actually, the delay of this combination logic determines the clock frequency, right? But if we use the processor chip for a long time, then the delay of this combination logic is increased. So which means that, so actually, when we design the digital system, we have this some time gap between the clock period and the delay of the combinational logic, and then this time gap is called slack. And if we use this processor for a very long time, then the slack is decreased because the delay is increased for the combinational logic, which means if the slack becomes negative value, then the circuit will generate the incorrect result. Okay. So this is called the permanent failures. So we use processor for a long time. So also think like the data center server system. So actually we do not turn off this server system, and then many users are using the data center servers. So which means the CMOS transistors are used again and again for a long time, and the CMOS transistors are worn out. So the properties are getting worse. So some circuits can generate the incorrect values. So these are also reliability issues. It is also true for the memory devices. So for example, the flash memory. So, we use the flash memory as the main storage media of the SSD, but so I believe some of you know that the flash memory has the limited number of erase count. So if we erase the same CMOS flash memory cells about 1,000 times, then we cannot use this CMOS cell because the cell is worn out. Okay, it's also a similar issue. It's some reliability issue. So we can categorize these issues as it's a hardware error, but we can classify that this is some errors like as the intermittent failures and then permanent failures. The permanent failures is permanent error. The circuits are worn out, and then we cannot fix this error. This is called the permanent failures. And then sometimes the errors can be influenced by temperature and then some other issues. So sometimes some circuits are in a very short time. Some circuits are frequently used, and this circuit may generate some errors. So this type of error is called the intermittent errors. Okay. So we may fix these intermittent failures in a circuit, because which means if we just do not use this part, this component, then the errors can be recovered. But permanent failures, the circuits and the components are permanently broken. In this case, we cannot use this device. This is also called the permanent failures. Actually, these type of errors are not applicable for the personal use because we do not use our computers continuously. So actually the workload, applied to our desktop computer or a personal computer is the amount of workload is very low compared to the data center. But for the server systems, the reliability issues can be very critical. Also, actually, as I mentioned, this reliability issue is also related to the ferrocide technology, the semiconductor technology, which means the size of a transistor is decreased, which means the reliability issue is getting more critical if we apply the smaller transistors. Okay. And then wire delay. Actually, the wire delay is determined by delay of metal layer. So actually, later we will learn about the transistors. But why do we apply the smaller transistors? Because if we make the smaller transistors, the characteristics, which means some speed and then power consumption. So these characteristics characteristics of a CMOS transistor is getting better. So which means if we make the smaller transistors, then we can make better transistors, which means faster and then consume less power. So it's good. But wire delay. CMOS transistor is just the semiconductor. It's a transistor, but wire is just metal. So it's metal like copper or aluminum. So the wire delay is just determined by the area and then the length of metal layer. Okay, actually, we can use barrel transistors if we use the smaller transistors, so it's faster and then the power is less consumed, but we cannot apply this scaling for the metal layer. So usually the delay of the metal layer is longer than the delay factor of the CMOS transistor. So that's why if the chip size is large, the delay of the wire this metal layer is critical for the performance. Okay. And then design complexity. You know, the current processor design is very complex, and then which means actually in order to make the whole entire chip, then we need to verify our design. So this is called the verification process. And then actually verification process is also very, very critical. So it means we need to invest a large amount of human resources to verify our chips. So as the chip design is getting more complex, then more verification efforts are required. So this is design complexity is some issue of the current processor design. Okay. Another issue is the CMOS. So Moore's law is ending. End of CMOS scaling. So currently, Intel is applying 10 nanometer semiconductor node, so CMOS node, semiconductor node. So which means that this node size means the width of the channel length, width of the CMOS channels. Okay, so actually we can understand that this node number is related to the size of transistors. So, and then as I said that if we use the smaller transistors, then we can use the barrel transistors. So characteristics of a transistor is getting better if we use the smaller transistor. This is the effect of CMOS scaling. So with the CMOS scaling, we can use the barrel transistors, which means we can increase the performance of the processor more easily. Also, we can reduce the power consumption. Usually dynamic power consumption, but static power, because static power is very critical. But static power is increasing actually. So this is very critical for the performance of a processor. But you know, the Moore's law is ending. So it means it's very difficult. It's very difficult to apply smaller transistors. So recently, I believe the TSMC or Samsung is trying to apply CMOS. TSMC is applying 5 nanometer technology, and then they are developing 3 nanometer or 2 nanometer technology. I think that's very, very amazing. Okay, so 2 nanometer and 3 nanometer and 5 nanometer, it's very small. But you know, the cost of manufacturing, manufacturing is increasing rapidly, which means it's very difficult to apply the smaller technology node. So also, we cannot decrease the size of the transistor at the atom level. It's not possible. So we are facing the end of CMOS scaling. Then what will happen? Which means it's very difficult to use the good processor, barrel processors. So many researchers are working for this. So some possible solution can be quantum computing or some different technologies such as the carbon nanotube or some analog computing can be also applied. But recently, in the architecture area, we are focusing on the domain-specific architecture, not the general purpose process architecture. So now the trend of the processor design or processor research is also highly influenced by this CMOS scaling and the CMOS scaling. Okay, but we need to remember that performance is the very critical part. So we can say that the performance and cost is the very critical factor. Okay. Okay. Also, okay. So I will stop here. So in the next class, I will briefly explain about the CMOS transistor technology. It's somewhat a low level knowledge in the actually for the computer engineering, computer science student. But if we understand the CMOS technology, then we can understand how to increase the performance or how to reduce the power consumption of the processor, because the processor is built on the semiconductor technology. Okay. So I'll stop here. And any questions? Okay. Thank you for your attention. Here in the next class, and then also this is the first class of the hybrid lecture, in-person lecture. So I hope I can see everyone in the future lecture. Okay. Thank you. There is no.
수고하셨습니다.
감사합니다.